over to this computer.
Oh,
All right, I'm gonna mute.
Is it
Like, can
working?
you guys see my screen? Yay, nay?
Yes.
Okay,
Yes.
fire. Okay, so let's get started. We're gonna be covering two mechanisms: the acid catalyzed hydrolysis and the transesterification. So, as we learned in class, one of the main things about this unit is reactions at the carbonyl carbon. You can go from a lot of different functional groups from one another. So that's kind of a lot of what this reaction is. We're gonna go from this amide group to this carboxylic acid group. So in order to do so, the reaction is going to be acid catalyzed. So we're going to go ahead and draw this out right here. Right, and to be acid catalyzed, we have floating in this solution this hydronium ion with a positive charge. So be sure to draw out all lone pairs as well, just so you know like what's going on. So the first step in this reaction is one of the lone pairs on the oxygen of the carbonyl is going to go ahead and attack this hydrogen. And the bond is going to go ahead and turn back into lone pairs onto this hydronium ion. And this is going to give you an equilibrium reaction, and it's going to look like this. All right, and be sure to keep your charges. There's going to be a positive charge on this oxygen. You're going to keep this remaining amide group here. And as we learned in class, this is going to be one of your proton transfer steps. I believe in previous exams, they sometimes will ask like, oh, how many proton transfer steps are in this reaction mechanism? So if you guys want to draw out the mechanism, keep in mind which steps are proton transfers because they might ask that on the exam. So once you get to this step here, you're going to have a lot of waters floating in the solution. And the next step is that this group is going to go ahead and attack here. But before that, there's going to be resonance that occurs. Low-key running out of room. But the resonance that occurs is one of these arrows or one of these bonds is going to go up here. That's going to form right here, this OH group here, and this NHCH3. And the positive charge is going to go right here. So it's very fair that they might ask you to draw all resonance structures as well. So do keep in mind that resonance does occur in between the mechanisms. So let's get back on track with this water here. It's going to go ahead and attack this carbonyl carbon right here. And then what that's going to do, it's going to go ahead and add right here. Wait, hold on. Sorry, I forgot to draw this arrow that goes up as well. Don't want any Texas carbons. So that's going to go up there. This OH is going to add right here. This N stays here, CH3, and an H right here. All right, so the next step, we want to figure out which one of these groups is going to come off. So obviously, we don't want to remove any of these guys because we're just going to go back in the backwards direction from where we came from. So we're going to be removing this amide group right here. So what's going to happen is that there's going to be floating hydroniums here, and this is going to go ahead and attack one of these hydrogens. This is going to come off here, make some more water, and this is going to be another one of your proton transfer steps. So now we get something that looks a little something like this. Sorry. The NH2CH3. It's going to be positive charge right here. And we're going to draw all the lone pairs. And what's going to happen is that one of these lone pairs here can swing down and reform the carbonyl, and this group is just going to pop off and leave into solution. That's going to form something that looks like this. The positive charge here and the OH here. So we're not quite done yet. We have a lot of waters in solution. What they can do is take this hydrogen. These electrons are going to swing back down onto the oxygen for another proton transfer step. And that's going to give your final product of a carboxylic acid and H3O plus. Right? Do we have any questions about this question? I can't see in the chat, so you can like shout it out. I'm sharing my screen. All right, fire. Let's go on to the next step, the transesterification reaction. So the transesterification reaction is a kind of exactly what the name implies. We're going trans across, or it's basically we're going across esters. So we're going from one ester to another. So we have this ester here going to this ester here. We're just adding a carbon group.
Sorry to interrupt.
Mhm.
Going back to the last one,
Yeah.
what happened to the other hydrogen on the water when it attacked that carbonyl? Because
Um,
the group attached is just an OH, but
oh, I think I see what you're talking about. Yeah, sorry. Like right here, you're talking about, right?
yeah,
Oh,
yeah.
that's my bad. Yeah,
Okay, so it
there should
is
be
the
another guy
water.
right here. Yeah.
Okay.
And then another one of the waters. Good catch. My bad. Is going to basically steal this hydrogen, and that's going to come back down. Yeah, I totally neglected that step, and that's going to turn into H3O plus in solution. Does that answer your question?
Yes, thank you.
Sweet. Sorry about that. Thank you. All right. So transesterification. This is typically going to occur with H2SO4 as well as H2O because it's going to be acid catalyzed like the other reaction we saw previously. So there's a chance that they may have you draw out the catalyst and the kind of arrows pushing regarding these steps. So I'm going to go ahead and draw that out for you guys. Um, my brain just stopped working. Um, yes, sorry, I forgot to add as well. In order to go from this ester to this ester, we're going to have to have an alcohol in solution with CH3, CH2, and OH because we need this guy to go in here and replace that guy. So one of the first reactions is going to occur is this CH3, CH2, O group. I just drew out the structure like this. What this is going to do is it's going to attack this sulfuric acid here. I'm going to draw that out as well. It's going to look like this. So this double bond is going to go ahead and swing and attack this guy, and that's going to go back onto this oxygen right here. And what that's going to do is that this is going to form this CH3, CH2, OH2 plus, and that's going to form this HSO4 minus. So one thing to know is that this is an acid catalyzed reaction, and if you guys might remember, catalysts will typically regenerate, so we can kind of expect to see this guy come back into play at the very end if they ask you to include like all products. So now we have this guy. This is going to be our guy that's mainly going to be reacting. Let's go ahead and draw this first ester here, CH3, and we're going to draw this hydronium ion as well. And kind of like the previous step, the first thing that's going to happen is that this lone pair going to attack the hydrogen. This is going to go back down here, right? And this is going to go right up here with the positive charge right here, OCH3. Okay. Um, so of course, as we mentioned before in the previous question, there can be resonance here among this carbonyl-carbon, but we covered that already. So I'm going to go ahead and not do that right here, but just know that there is resonance that does occur. So now what we have here is this OH group here. Let's see, CH3, CH2, OH. This guy is basically going to come up here and attack this, and this is going to go up, causing this reaction to occur. This is going to go up here, OH, OCH3, OH, CH2, CH3 plus. The lone pairs here, right? So now what's going to happen? We have this tetrahedral intermediate as well. So we got to figure out what we're going to be kicking off and what we're going to be keeping. So since we're going from one ester to another, we're going to be kicking out this guy, and we're going to be keeping this guy right here, right? So we can do you can use water or you can use any convenient base. This guy's going to attack right here. It's going to go right here, and then this is going to reform this group right here. O CH2 CH3 O CH3. So this is really terribly drawn. So now we want to get rid of this guy. So as we have acid hydronium ion floating in solution, it's going to attack right here. And this is going to get protonated. I'm running out of space. Oh no. O CH3 plus O CH2 CH3. So now what's going to happen is that these lone pairs up here, it's going to swing down to reform the carbonyl, and this guy is basically going to leave in solution and just form this CH3OH in solution, or methanol. So another equilibrium reaction. You have this right here, this positively charged oxygen, and this guy's going to leave. So now we have this OCH2CH3, and finally, um, we need to get rid of this hydrogen here. So we can use any convenient base, or we can use water, whatever you guys would like. It's going to attack this hydrogen. This has one too many lone pairs. This is going to come down. And then over here, the final reaction is going to, or the final product might look like this. CH2, CH3. And keep in mind that throughout all of this, you instead of using water, you could use HSO4 if I'm not mistaken. But just keep in mind that that's going to be sticking around in solution as well if they ask you for like everything, because keep in mind the catalyst is going to not disappear. It's going to stay in solution. All right. Does anyone have any questions with this reaction?
Uh, did you mean to use the alcohol chain at the start to react with H2SO4 instead of water?
For which step? Sorry.
For the first thing you did before you even did the first reaction, you reacted
Yeah.
the alcohol with H2SO4 instead of water.
Yeah. I think that was just kind of showing you like what is occurring in the reaction before it even happens. Because this one of these guys, let me see. Um, I have that in my notes. I don't know where that comes off of. Let me see. H2SO4. I have that in my notes. I low key. If anyone else wants to chime in, my mind is totally blanking of why
It
this is
doesn't really matter if you
relevant.
use the ethanol or the water. The point is they provide
Hmm.
a source of acid so that basically where Austin has the water drone as hydronium, if you replace that with the protonated ethanol, it acts the exact same way.
Same
Either
thing.
one of them will pick up the hydrogen from the H2SO4. It doesn't really matter which because they end up doing the exact same thing.
Okay, and then could you also use HCl instead of H2SO4?
I think the reaction occurs with H2SO4. Let me see.
Yeah, I couldn't, maybe it could. But for our purposes, we're going to go with
I'll
use
stick with
H2SO4.
H2SO4. Yeah. All
Okay.
right. Any other questions regarding this section? Good questions. All right. Thank you guys. I'll hand it off to, we're going to cover reactions now.
I think that means I'm up actually. So y'all have to give me have a second. I'm sorry. Wait, my laptop's a little busted, so this is gonna take me a second to actually get it set up. Hope everyone had a good break. And I hope none of you were caught in that traffic yesterday. That was absolutely like atrocious.
I was. It was ass.
I'm so sorry. All right, share screen. We're gonna, yeah, we're gonna share that. All right. Can you guys see my screen okay?
Yes.
Okay. Does this let me write on it? Does my pen work? Oh, that's gonna be real fun if it doesn't. Um, oh, wait, it helps if I can. All right, looks like we're gonna be doing this with my mouse. I'm so sorry. Okay, so I'm gonna go through the reactions and I'll skip over the mechanism parts of it. But we're gonna go bit by bit and just show like what happens after each individual step and what it looks like. So first things first is we're gonna look up here, and this is our Wittig reaction. It's one of my favorites, honestly. So we have phosphorus with three phenols on it, and all it's gonna do is we're gonna have a nice little easy SN2 reaction. So we get our, oh, this is gonna look so bad. I'm so sorry. So we get that where it's literally just replace this bromine with this over here attached. Now our N-butyl lithium here, um, all we're gonna do there is that's going to act as our base because that lithium is going to come off and we'll have a very negative thing. And it's going to take a hydrogen from this carbon right here. So we're going to lose that hydrogen and instead gain a negative charge on it. Oh, and here this should be positive right now. So we lose that hydrogen, get positive on it. Are you really not going to work pen? I'm sorry, I'm going to give the pen one more try because it's going to save a lot of us pain if I'm not using a mouse to write this all out. All right, well, that didn't work. So after that, we just take this proton off. So we go ahead and erase that. And now we have a, that's okay, cool. So one pair here and a negative charge. So once we have those things, now we're going to take our acetone, which is just a nice basic ketone. And we're going to form kind of a little box structure using the carbonyl and this carbon phosphorus. So we get our P PH3. Oh, that's so bad. I'm so sorry. To carbon to our carbonyl carbon, our oxygen, and then that's bonded over to there, and then we have our two carbons coming off of this. So now we have this as a little intermediate, and what's going to happen is these bonds are going to break. That goes up there, and this one comes down here, which gives us our final product of how many carbons are coming off this too. Gives us our final product of, give me a second. It should have 1, 2, 3 from our acetone, and then 3 carbons from our bromopropane to start. 1, 2, 3. Perfect. So all we end up with there is creating a new carbon-carbon double bond. And that's the biggest thing that we get out of our Wittig reaction. So now here on this part, what we're going to do is we're going to take the lithium aluminum hydride, and that's going to very quickly reduce everything, and it's a strong one. So it's going to be our H minus. It's going to go and it's going to attack this carbonyl here and this one here. Basically turn this into the arrows. So to go and I'll attack there, and what happens is because we're already in a basic solution, we end up forming yeah, sorry. So we're going to attack these and we'll get our intermediate. Where these oxygens are now single bonded and are negative. Make sure you include your lone pairs. There should be 3 on all our negative oxygens. Should also only be 2 on that hydroxide over here, but I'm not going to worry about that at the moment. Once we have that, we just react with HCl, and what's going to happen is it's going to reduce this left oxide over here into an alcohol, but on the right side, we're actually going to turn that into just a primary alcohol. So we're left with my carbons are 1, 2, 3, 4, 5, 6. Yep. Secondary and a primary alcohol. So your lithium aluminum hydride will turn ketones and secondary alcohols and carboxylic acids into primary alcohols. A reason this occurs is, we'll turn. I'm actually not sure I have an answer for that, but you just gotta know it turns into a primary alcohol for the carboxylic. So moving on, we're going to do roughly the same thing, but this time we're using sodium borohydride, which is a more tame version of lithium aluminum hydride. So what we're going to do is, because it's a weaker version, we're only going to attack the ketone over here. But aside from that, business as usual with what we did at the top. So we get carboxylic untouched. Pretend that's an oxygen. And also pretend that's correct in the right spot. Yeah, there we go. Secondary alcohol. Any questions on any of those 3? No? All right. So then we're gonna, no, that's nice actually. Why is it doing it this way? Oh, I see why. Okay. So you guys are all good with these? I'll redraw the products for these really quickly, in a way that they actually stay where they're supposed to. But for the moment, do that. And I'm gonna go ahead and do the dartboard. All right. So here we go. 2 double bonded 2. And we're H negative oxygen, negative oxygen, and then okay then. Okay. So moving on. Now we're looking at toluene here, and we're going to react it first with our Br2 and a light. So what that's going to do is it's going to basically form a radical, and then we'll add a bromine onto this benzyl carbon here. So just gonna do a circle because it's way faster. Then we get our BR. Well, hold up. Not quite. Bond over to the BR. And then once we react it with the magnesium and dry ether, that'll just kind of insert uh, magnesium in between the bromine and the carbon. So instead, we'll have, oh, that's a really bad M, MgBr. And what this acts as is basically putting a negative charge onto the carbon, as magnesium's not very high electronegativity. So now we can use this as our nucleophile, and we're going to react it with this one over here, and we're going to attack this carbonyl. So once we've done that, we'll go there, we go negative, hydrogen coming off, and then our carbon plus the benzene ring, which I'm going to abbreviate as pH to save us all some time. Then fourth step, just a nice easy acid workup. So all we're going to be left with is having this as an alcohol. Sorry, excuse me. All right. Any questions on that one? No? Okay. I also can't see chat, so if you have something in chat, feel free to say something or at least tell me to go look at it. So, all right. Now looking over here, we got the same thing that we just had with a Grignard reagent, which is when we see the MgBr. So we know that's going to be our nucleophile. And as usual, we're going to go and attack our carbonyl. That's right here. The difference is this time we have a good leaving group. And also to make it more clear what we're doing, we're going to say that we have two. Okay, can we? Two of this molecule here. So we're going to attack that first time and we'll get our, oh, these are just rings. So we're going to get 1, 2, 3, and then we go oxygen there. So we get, or after the first addition rather, I'm just going to skip to that. After the first addition, we get our ring, but we still have a carbonyl and we have a second nucleophile that we can use. So then we move on and we get another addition of it. So now we have our negative oxygen and then 2 of our rings. And now that we don't have anything else we can interact with that nucleophile, we're just going to do an acid workup and turn that negative oxygen into an alcohol. So we'll have to 1, 2. That's vaguely a hexagon. And then for this last one, I'm going to be doing roughly the same thing, where this one is just a transesterification like we saw earlier. So after that first one, we're going to go in with our oxygen being our nucleophile. We're going to attack carbonyl down here. double bond's going to go up, come back down on a second step, and our ester here is going to leave as ethoxide. And that'll give us and then we have an isopropyl group coming off of the secondary alcohol right here. So we got that. And then this H here is just an acid catalyst that helps make this progress. So to start the reaction, this would probably get H first. It's the same mechanism that also just went over. So like getting H first, it goes up. And then when it comes back down, this gets protonated at some point so that it can come off as a better leaving group. Any questions on those last two or on any of the other ones? No? All right. I think I'm going to pass it over to Tanner then. Thank you.
All right, let's move on to the second portion of our reactions. Let's make sure I'm opening the right one here. Let's see. Right. Yeah. Okay, perfect. This is not the key. Okay. These should all be familiar, right? This one, whenever I look at these reactions, or if like I'm given like one-step reactions like this, I always break down what I'm looking at here. And so in this case, we're given NaOH, and the key thing here is that we have OH, which is a strong base, and then we've got our acid, and we've got an ester. Pretty much these three things are going to combine into a saponification, right? You guys should be comfortable with the idea that our strong base, acid, and ester combination will be a saponification. Here, in this case, we are just turning this ester into a carboxylic acid, right? Moving on to number 8. By the way, if anyone has any questions, please interrupt me. I'm just going to keep on moving through these to keep it punctual. But moving on to number 8 here, breaking this down again, we've got an alcohol, in this case, ethanol. We've got an acid, which is just H3O plus, and we've got an amine or an amide. So in this case, we have our OH group on an alcohol, and we have our amide. We're going to get a substitution. And in this case, since it's a ethanol, we get this style of replacement. That is not a 5. It's a 3. And by the way, a more clear version of these final products will be available when the key is posted. I'm limited by my ability to draw with a mouse right now. So hopefully everything will be clear for y'all, but we should be just grasping the general idea of these reactions to prep you guys for this exam. And general idea here is recognize what you're given in both your reactants and whatever you're given in this reaction step, because everything here is a reactant, but right, breaking it down, alcohol, amide, in this case, acid catalyst, H3O plus, we're going to get that replacement of our amide at that nitrogen, turning it into what our alcohol was. Now, moving on to number 9, we have cyclic amide with a strong base, CH3, CH2Br, and then HCl, H2O, and heat. Now, we did this one a couple times in class, if I recall correctly, but it should look pretty familiar. And like the idea that we're going to be breaking open the ring at this section. And so I think this one was on the homework, and that's why it looks more familiar than maybe some of the other ones. But there's not going to be any reaction happening over on this benzene side. Just going to make like that. But when we break open this ring, we're keeping our ketones. Well, I guess they're not really ketones. We're keeping our carbonyl bonds here, right? These aren't reacting here. Whole reaction site is this nitrogen. And so on the end of this, we get two carboxylic acids on the, wow, that was bad. Two carboxylic acids when we break open that ring. And in this case, whenever you're given like reaction questions like this, they really only ever ask you for uh the major product, but we do have a little byproduct over here due to our second reactant here, CH3, CH2Br, which just will grab up that amide nitrogen. So just recognize the ability, or just have the ability to recognize that when you have this cyclic amide, you're given a strong base, you're given this brom bromine carbon chain and HCl, H2O, and some heat. You're breaking it open and you're getting some carboxylic acids on both sides. All right, moving forward onto number 10, we've got this anhydride structure. And so we're also given water to react with it. Looking at this with an anhydride, break this down. Sorry, my notes are a little scattered on this one. All right, breaking this down, we've got OH over here, or I guess H2O. But we've got two. Sorry, my notes are a little confusing for me. I want to make it look a little nicer here. We have H2O, right? Looks like this. Still got lone pairs on this oxygen here. We're going to get this style of attachment. We're going to this carbon on a carbonyl, and we're moving some of these electrons on this carbonyl bond up into the oxygen, and we get this attachment. Since this one's a little more involved, we'll be going step by step to get to our final product. Oh, that's why my notes look weird, because it's not H2O, it is OH. Why did my lone pairs disappear? Sorry, y'all, this is a little technical difficulties. Okay, so this is some intermediate product we have here, and we'll have H plus in solution. This is OH minus, just how water breaks apart into its individual ions like this. Now we'll get the break of our interchain oxygen. And in this case, it's coming from our electrons that we moved away in that initial step, coming back down to reform a carbonyl. We're using some lone pairs on this central oxygen, grabbing a H plus ion and removing part of the chain here to make everything stable once again. So that means when we do get this breakage, we're going to get a very short carboxylic acid and one slightly longer carboxylic acid. Okay. Now, moving forward on to number 11. These should look familiar from today, right? If we have, I'm gonna draw out some lone pairs here. We're just given heat here, but we have a dicarboxylic acid chain. And so this comes from the case of counting out your chain, right? So in this case, we are going to get cyclic formation. That's all that we did today in class. And so if we count this out, 1, 2, 3, 4, 5, 6. We get the movement of these electrons to this carbonyl carbon, and these come up into the oxygen. We will get a six-membered ring. So in this case, it's going to look a little ugly, but everything else does. Now, this isn't our final product right here. This is just an intermediate to show out that we should keep counting along the way to make sure that we are where we want to be. So if I'm going to change my color real quick. 1, 2, 3, 4, 5, 6. Now, these correspond with what we counted out on our original chain here. So it looks like we're in a pretty good spot. And now we just have to clean up this little mess here where we get the removal of this OH group and some of these lone pair electrons on this negative oxygen come back down to form a carbonyl. And we'll get the cleaned up version of cyclic anhydride. Yeah. Now, moving on to number 12, we have an alcohol with some acid, dibol H, which is a special reagent here, and H3O plus. Now, anytime I see dibol H, my little trick to remember what it is used for, dibol and aldehyde. Al and dibol, Al and aldehyde. That was a little trick I had to memorize this stuff. But in this case, got a carboxylic acid, dibol H, alcohol, HCl, H3O plus. Simple formation of aldehyde. All right. And now one of my, now this is confusing. My key here doesn't have 13 and 14 on it. My problem, my blank here does. Hmm. Let's see if I can hunt down the other one. Any other TAs know if I downloaded the wrong one here? Oh, hold on. I'm gonna stop sharing my screen for just a moment to hunt down this.
Yeah, I don't see it on my end either. I'm not gonna lie.
Okay. Let me see if the announcement posted Do you guys have 13 and 14 empty on yours, or is that just on our key that seems to have lost 13 and 14 on it?
We have it.
Hmm, interesting. Don't know how we lost a page here. Tamaj, do you have the other key? Let me see if I can hunt it down here. Found an old one.
Do we want to jump to nomenclature and we can come back to this? Or did we cover that yesterday? I
We
wasn't there.
covered it yesterday, I think. Yeah, we covered it
Both
yesterday.
pages of nomenclature?
Um, hold on. I think there's like one more page left of nomenclature.
Is it like the second page that starts with 15 going to 28?
Yes.
We didn't cover that one yet?
No, not yet.
Okay. We can cover that and we can find these missing questions because that is really flipping weird.
I had a question for number 10 on the reactions. I didn't want to interrupt you. You can kind of fast through them, but
Question 10.
Yeah, of course. What's up?
question 10, I feel like wait, I think did you have an extra carbon by any chance or no on the
Oh, yes. Hold
and
on.
then
Yeah, because there was one that was 3 carbons and one that was 2 carbons.
yeah.
Yeah. They should both be 2 carbons because it's in that the breaking of that central oxygen, you
Mhm.
only have 2 carbons on both sides.
And then would it make a both alcohols? Because on the reaction summary it says that it makes one alcohol and then one with a negatively charged oxygen.
So both do occur like that. However, in most cases, like since we are reacting this with water, we're going to have excess hydrogen in solution. So having in that case, it would be a carbonate uh, ion. They truly do happen like that, but they will like very shortly after be stabilized with a hydrogen and both become carboxylic acids. So both
Okay.
answers are correct.
Okay.
All right, I can cover the second page of nomenclature if you guys are ready for it while we try to find these last two questions. Let's see. Okay, can you guys see my screen? Okay. So picking up from yesterday, so we have this first structure right here. This is going to be a 6-membered ring. Remember, we're going to be counting the heteroatom as well. Um, so we know this is going to be a cyclohexane of some sort, right? Sometimes it might be kind of confusing if you guys, I know a lot of you guys will accidentally draw out cyclohexane instead of like benzene, for example, but just keep in mind that those are two different molecules. So we're going to go ahead and put down cyclohexane. And so when we start here, we're gonna start the heteroatom right here. The nitrogen gets the number 1, and then we're gonna see whether we go left or right. So in this case, we're gonna be going left because that's gonna give us the lowest number. So it's gonna go 1, 2, 3, 4, 5, 6. So once we go that way, we can start naming. So this is going to end up being 3-chloro. And this methyl group is coming off the N. So this is going to be N-methyl. And the important thing to know about nitrogens in the middle of a ring is it's going to have a special name we don't want to omit. It's going to be aza, so AZA. So this final name is going to be 3-chloro N-methyl aza cyclohexane. All right, so let's look at question number 16. So right here, it's going to be really tempting to start the name off the benzene because that's like what's going to draw your guys' eyes and attention. But keep in mind here that the aldehyde here is actually going to take priority and that benzene is going to fall onto a branch chain. So we're going to start numbering right here. 1, 2, 3, 4. So this benzene is going to come off of the 4th carbon, which is going to turn into a phenyl. So it's going to be 4-phenyl. Don't forget that. That's might show up on the exam. And we have a 4-carbon chain, so it's going to be bute. And it's going to end in, sorry, it's going to end in an carbonyl group that's terminal, which is an aldehyde. So it's going to be butan-al, with an Al here. Okay, so let's go into question 17. Very similar principle to 15. We're going to start numbering at the oxygen. And now we're kind of stuck. Okay, do we go left or do we go right? So in this case, we're going to actually be going to the left because even if we go the other way, it's going to be like a 1, 3, 5 naming designation. So we're going to have to look at alphabeticals here. So in this case, the 3 being the lower number and being bromo is going to take priority. So the final answer is going to be 3-bromo and then 5-hydroxy. And then remember above we mentioned that because there's an N there, it has to be aza. If you have the oxygen as a heteroatom, it's going to be oxa. So don't forget that. Oxa cyclohexane. Okay, sweet. Now we have 18. So not to get confused from before, now we're working with benzenes. So we have to remember the common names as opposed to just cyclohexanes. So that big chart that you guys had to remember of the common names, please don't forget that because as you guys see here, it's coming back. So what I like to do is I like to circle the main parent name. In this case, this is going to be the group here, and this is going to be called anisole. And because this is the parent, this is going to get designation number 1, and the chlorine is going to fall to number 4. This is quite easy if you guys remember it. 4-chloroanisole. Okay, now let's go to number 19 here. This is a straight chain molecule, so no, we're not dealing with any rings. So let's just find the longest parent chain, and it's going to be this guy right here. And we're going to start over here with number 1, 2, 3, 4, 5, 6. So this is going to be the main parent chain ending. So the OH is going to start off by turning into a prefix as 5-hydroxy. And then we have a 6 carbon long chain, so it's going to be a hexene of some sort. But this group here with the carbonyl and this chlorine is going to turn into hexane oil. This oil here is very characteristic of this OCl. And please leave a space here as well. And then fluoride. Okay, so now we're going to go to number 20. Another straight chain molecule, we're going to find the longest parent chain, and it's going to be this guy right here. And we're going to start naming from this carboxylic acid group because that takes priority as it's the lowest number. Another 6 carbon long chain. So we know that this is going to end in an oic acid of some sort. Oic acid. And now we also see here we have a number 5 or an iodine on number 5. So this is going to be iodo. I can't spell iodo. And also keep in mind that there is a double bond spanning this molecule. So we need to remember E and Z designation. So in this case, this is going to be E designation. So it's going to be E, always up first, dash 5 iodo. Then it's going to be hex. And remember, we also want to like designate which carbons the double bond spans. And it's going to be the lowest of the 2 carbons it spans. So it's going to be hex dash 3 dash ene oic acid. All right. So now let's go to question number 21. So we have another benzene here, and whenever you see benzenes, try to recall the memorized common terms you guys have. So in this case, we have either aniline or phenol, and in this case, phenol is actually going to win in this case, so this is going to be number 1. And then obviously we're going to want the lowest numbers, 2, 3, and then 4. So naming this, it's going to be going in alphabetical order. So we're going to have 4 amino before 2 bromo. 4 amino dash 2 bromo phenol. Sweet. All right, we're halfway done. Any questions thus far?
For question 19, sorry.
Yes. Mm-hmm.
You said that hexanoyl
Mm-hmm.
says is because it's with the chlorine on it.
Yes.
Would adding a chloride space with it be like redundant or no?
Like the space right here.
Yeah, like since it already says that hexanoyl is I forget the name of it, but with the chlorine on it, would
Uh-huh.
adding chloride also like just be redundant? I don't know if I'm making sense by saying that,
No,
but
I understand. Like as opposed to like just keeping
just
hexanoyl versus
yeah, because it's saying
hexachloride.
that because it's already saying it's in the parent chain, if you know what I mean.
Yeah, I would keep it there because if you just put hexanoyl, you're not designating the halogen. So it could be hexanoyl bromide,
Okay.
hexanoyl iodide or whatever. So
Okay.
just keep in mind that we want to keep in mind like what halogens there. So hexanoyl chloride.
Okay. Thank you.
Mhm. All right, so let's move on to question number 22. So same thing as before, we see this this benzene here, which we want to. It's very tempting to make it as the parent and name this as a whole side chain. That's going to be a pain in the neck. You can quickly find out. So this is going to actually be a straight chain carbon as the parent chain. So we're going to go ahead and highlight this, and now we're either stuck. Do we name it going from 1 to 3 going this way, or do we name it 1, 2, 3 going this way? Wait, 1, 2, 3, 4, 5, 6. Oh yeah, so we're stuck between either going this way or this way, one way or the other, and this comes down to priority. So the OH is going to be taking priority here. So in this case, it's going to be with the pink naming. So I'm gonna go ahead and erase the blue. So it's going to be 1, 2, 3, 4, 5, 6, 7. So 6 phenyl, and we have a 7 carbon long chain. So it's going to be and it's going to be 2 ol, because that's where the alcohol comes off of. So now we have question number 23. It's another straight chain, which looks kind of funky, but this is going to actually be a straight chain. So we're going to go ahead and name it from right to left because the ketone here is going to take priority over the 2 methyl groups. So given this naming, we're going to go ahead and name the methyls 3, 3. We want to keep in mind there's 2 methyls, and don't forget a di. Dimethyl, and it's a 4 carbon long chain, so it's butan, and then ketones are always going to be in the center, so 2-on. Okay. So now moving on to question 24, we have this amide-like group here, which looks really scary to name, but if you break it down into pieces, it might be a little easier. So we're going to always start at the carbonyl-carbon right here. This is actually going to be a parent chain, so we have an ethane of some sort, or an ethanamide. So we have this as your parent chain, and then naming these guys here. This is going to be 1, 2, 3. This is going to be a prop group or propyl group. This is just 1, 2. This is going to be an ethyl group. So naming the full thing, it's going to be N-ethyl, N-propyl, ethanamide. All right, and ethyl goes before propyl because of alphabetics. All right, sweet. So now we have question number 25. This is going to be a cyclohexane. It's not going to be a benzene, so please be careful. I feel like I sound like a broken record, but it's something to keep in mind. So we have this OH group here and this CHO, which a lot of people might get confused by, but this is just like a sneaky way of writing like an aldehyde. So it's just going to be this. If it's a C like OOH, that's a carboxylic acid, but because it's just CHO, this is going to be an aldehyde, and that's actually to take priority of being number 1. So this is number 1, this OH para to it. We're not benzene, so it's not para, but this number 4 is going to be where the hydroxyl group is. So this is going to be 4-hydroxy cyclohexane, and keep the E. Typically we do hexane, but this is hexane, and then it's going to be carbaldehyde. That's just something you got to know. Like whenever you see the aldehydes, it's going to be carbaldehyde. So now we have question 26, another kind of scary looking thing, but if we break it down, it's not the worst thing in the world. So, so right here we have 1, 2, 3 is going to be your parent name. So this is going to be a prop of some sort. And because this is an ester, this group right here, not an ester, actually, yeah, an ester. I'm tweaking out. Ester? Yes. Okay, yes, sorry. It's going to end in O8. So we have a propanoate of some sort. And we can go ahead and just name this out already. So 3-amino propan, running a space, propan O8. All right. So now we have this side chain here coming off of the oxygen, and we're going to find the longest parent chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we're kind of stuck at a crossroads here. I think that this is going to be the right way, because if we end up going like this, we're going to have a branched branch, which is a pain. For some reason on my answer key, I don't know what's going on, but this is actually not there. So on my side, this is what I have. So I don't know what's going on with our answer keys today, but I'm just going to go ahead and name it as this group here, but I could just totally be tweaking. Okay, yeah. So this is going to be a hexyl group here. Wait, 1, 2, 3, 4, 5. Yeah, a hexyl group here. And then naming off here, we have a 1, 2, 3, and this is 4. This is going to be 1, 2, 3 prop, and this is going to be 1, 2 ethyl. So this is going to be A. I went through that kind of fast, but ethyl is going to be here because we have 2 carbons. This is going to be 1, 2, 3. This is propyl. So it's going to be 4 ethyl dash 3. I have no more spatial. The propyl hexyl space 3-amino propanoate. On your end, I don't know what you guys are seeing, but for me, this is just what's on my screen. I don't know what's going on. So let's move on to question 27. We can talk about that later. So 27, another kind of scary looking molecule. But if we break it down, we see that this is just a dioic acid, carboxylic acid this side, carboxylic acid this side. So it doesn't really matter which way we number it. We have 1, 2, 3, 4, 5, 6. So it's a hexane dioic acid. That's going to be our ending. Hexane, because there's 6 carbons. We keep the E because there's a dioic space acid. right? So now let's deal with everything in the center. So we can either choose to name from right going to left or left going to right. So we're stuck between either a methoxy or a hydroxyl. And in this case, the hydroxy is going to take priority. So we're going to name going from right to left. So it's going to go 3 hydroxy dash 4 methoxy hexane with an E, dioic space acid. All right, and finally here we have a benzene, so we want to keep in mind of our parent names. And in this case, this SOH3, this is going to be a sulfonic acid and parent chain, a parent name. Sulfonic acid, I'll put that in the space. So now we have that, so this is going to take number 1. And now we're stuck with the same predicament going left to right or going right to left. So in this case, we're stuck between a bromo or a 1, 2, 3, a propyl. And in the alphabet, obviously B comes before, so this is going to be 3 bromo. 3 bromo dash 5 propyl, and this is going to be benzene sulfonic acid. I forgot the benzene part. You guys are probably shouting at your screens. Benzene sulfonic acid. All right, so that covers the latter half of nomenclature. Does anyone have any questions about these questions? All right, sweet.
For
Oh.
for number 27,
Mm.
do you want us to number the benzoic or the carboxylic acid groups?
It's not necessary to number the carboxylic acids in this case because carboxylic acids are always going to be terminal. And with a dioic acid, this is the type of stuff you're going to see. So it'd be redundant to put like 1,6, for example, because you know it's a hexane dioic acid, you know it's going to be at the end of your chain. So you don't need to put numbers there.
Okay, cool.
Of course. Any other questions? Sweet.
All right. I've hunted down the correct version of our key here. All right. We're back to where we were. And we can close up this review session with these last two here. So breaking down number 13, right? We've got H2O and HCl with a ketone. Now, this can be a ketone, this can be an aldehyde. Either option here will get us a very similar result where we are going to get a gem diol. And so, gem diols, 2 alcohols on the same carbon. In this case, we're going to get it to look like this. Now, I'm not sure if they're going to want you to know that you do have some stereochemistry come in with this, but I feel like it's kind of useful to know this. So, looking at this, H2O and HCl, we'll get the protonation of our ketone, and we'll get the addition of an OH group. So now we have 2 OH groups on the same carbon, giving us a gem diol. All right. Now, number 14, we've got a diol. We've got lithium aluminum hydride. Whoops. And we have HCl. Now, this concept is a protecting group. And in this case, we're going to use this diol to protect our ketone all the way over here. Our ester group is going to be our reaction site for the rest of this. And our protecting group, just to kind of know what they look like is helpful, is if we just isolate this ketone over here, the protectant group is going to react in a way that will look like this. It's kind of sloppy, but this is our two oxygens from our diol, 1 and 2. And then their two carbons up here, 1 and 2. This protects our ketone from a strong reducer. And so in this case, when we get this protected group and we react with a strong reducer, our ester will be the only thing that reacts. So in this case, our final product, once we remove that protecting group that we added for our ketone, we get our ketone back. And if I count my carbons correctly, even though it looks really just messy, our final product should be this lone alcohol after this ester reaction. All right. Any questions on these last two before we open it to just general questions? I don't know if I can see the chat right now. Hold on. All right. Well, I'll stop sharing my screen now, as this was the end of, I think, everything we had planned to cover tonight. So the review session recording will be uploaded and a cleaner version of the key as well.